Alright guys, Mr. Yenna here. We're going to be going through measurements, notes. You guys should have just finished the reading on this section in your Nature of Science portion of your book. That's right in the beginning. And now that it's all done, I kind of want to go through and sum this up in one nice neat little sheet of paper called your measurement notes. And then you guys will hold on to these. You'll turn them in and get points on them, but you guys will have these to look at and to use because we're going to go through and we're going to break down basically every type of measurement that we're going to discuss. So this is a page, this is what your page should look like here. It says measurement notes. If you're in 8th grade, you should have a sheet that looks a little bit different than that. It should actually underneath measurement notes say 8th science, and then that little table that you see there with the metric system, yours should be a little bit more complex with some blanks because the 8th graders are going to be working a little bit more with the metric system. Okay, so before we go ahead and get this started, if you could, as a class, and I'll let the teacher go ahead and run this how they want to, but go ahead and make a list of different things that we measure. And I'll go ahead and give an example. You might say that we measure height. You might write that on the board. You might even say the units that we use, because here we use feet and inches. If you go to a different country, chances are they probably use the metric system, and they would say how tall you are in centimeters or millimeters. So it's very different, right? So go ahead and take a few minutes and discuss that. Okay, I'm going to assume you guys already discussed that. Maybe you wrote stuff out on the board. And what I'd like to do is, as we go through these measurement notes, we can go ahead and see if we've hit basically everything up there on the board. You may have things that that you said that were not correct, or you may have things that were other ways that we can measure that we didn't actually include on the notes. But I'm just trying to do the most important things on the notes that we measure, and like I said, eventually, or this next week and a half or so, we're going to be measuring all these things. Okay? So let's go ahead and start at the top of the notes, the measurement systems. This is my PowerPoint. I will post this on the website as well, but I'll step you through this, and if you need to pause it at any point because I'm going too fast, please go ahead and pause it and then pick up, okay? So, measurement notes. We have many different ways to measure things. If we didn't have rulers, meter sticks, tape measures, odometers, some of you don't know what that is, or other things like that to measure distance, how else could we measure? So that's really a tough thing. You know, we might say something is far away or something is close. But that can be very relative. My idea of far or my idea of close can be very different than your guys's. Or I may say, man, that guy was really tall. And I think to most of you, you'd probably say, yeah, he was really tall too. But I might say, that guy was really short. And some of you would say, hey, he's taller than me. You know, so to you, he's taller. So we have to have some way that we measure things, that we quantify it, meaning we put a number with it. Because then it takes out the whole, oh, I think it's tall, or I think it's short, or I think it's far, or I think it's not very far. It takes that all out of the equation, and then we just have a number. And you can interpret that how you want. You know, 5'9" to some of you might be really tall, and somebody like me, someone who's 5'9", may not be very tall. So we have two main systems of measurement. The first one is called the Imperial System. That's the one that we use. It was created by the British in 1824, and we have all these different units like inches and feet and yards and miles and gallons and ounces, and these are all different measurements that were started in Britain. There's a lot of problems with it, as we'll get into in a little bit. However, most of us are set up on that whole system just because we live in America and we know how much a gallon is because we buy gallons of milk. Or we go to the gas station and we get 5 gallons of gas or something else like that. So that just makes sense to us. We can visually see like a gallon jug of water or a gallon jug of milk. And if I say a liter, we may have a harder time with that. Some of you, also we have 2-liter bottles of pop and stuff, so you might do a little bit better with that. But a lot of those other metric system measurements we have a hard time with because we don't often see them represented using the metric system. So then that's the second system, the metric system. It's abbreviated as the SI, and that's because in France, a lot of other countries, they switch the order of some words, right? So the adjective would come first. So instead of saying the international system, like we would say, they would say the system international. So SI is what it's called. And it's the official international system, first adopted by France in 1799. When I say it's the official international system, what I mean is basically the whole world uses it except for us. So we're going to get into why that's so important and why the metric system is a really awesome system. Again, most of us are shaking our heads saying, no, it's not. I don't want to learn metric system just because we're not used to doing it. But pretty much everyone else in the whole world uses it because it makes sense, and our system stinks. It doesn't make much sense. Oops, wrong way. All right, so this is our metric system, and if you can look at your chart there, yours looks a lot like mine that's posted here, a little bit different. 6th and 7th graders, again, yours just has a little table and you don't have any blanks to fill in. So you guys can scoot through this section real quickly. 8th grade, you'll probably need this pause for a minute so you can record some of these things. But I tried to put on your paper the ones that are most important, meaning the ones that we see most often. They're most used by us, and for 8th graders, the ones that I'm going to have you guys learn so you can really understand it, because we do see it pretty often if we're actually looking for it. So in the left-hand column, 8th graders, you have abbreviation, right? So we can see the abbreviations are just one letter. Some of them are capital and some of them are lowercase. That's actually really important, okay? Because if you look at mega, what's the abbreviation? It's a capital M. And if you look at milli, what's the abbreviation there? It's a lowercase m. So there is a big difference there. If you're meaning to say millimeters and you write a capital M next to meter, now you've just said megameters. And if you look at that meaning there, you see the number, there's a big difference there between that, okay? So you have to be really important about capital versus lowercase letters when we're dealing with abbreviations in the metric system. So let's just go ahead and start with kilo. 8th graders, I already filled in your info there for abbreviation and scientific notation and all that. But when we say kilo, K, what we mean, and it says meaning there, is in this case it has it represented by scientific notation, 10 to the 3rd power, right? And if you put that in a calculator, 10 times 10 times 10, it equals 1,000. So 8th graders, on your paper, it says 1,000 at the top. So if I said kilometers, what I mean is 1,000 meters, okay? So it says meaning 1,000. It's telling us how much of that unit. So kilo is not a distance, it is a number. And then the thing that comes after it is what we're measuring. So if we're saying kilometers, we would say km, and then we know it's 1,000 meters. It could also be a different measurement, not meters, not a distance, but something like mass or weight, right? So we say, oh, I weigh 200 pounds in America, if that's how much you actually weigh. If you're in a different country, they wouldn't say 200 pounds. No one would have any idea what you're talking about. They would say, I weigh 85 kilograms or something, right? So now we're talking about a weight, or more like a mass, right? And so that's a different measurement, and we're dealing with the unit of grams. So when we say a kilogram, we're talking thousands of grams, okay? More on that stuff later. What I'd like for you guys to do is just kind of go through and fill some of these things in now, okay? So we've got hecto. The abbreviation for that is not actually on here, but the abbreviation should be H, okay? It's lowercase h. And so hecto, again, that deals, since it's the prefix, it deals with any type of measurement. It could be a hectogram, which would be weight. It could be a hectometer or hectometer, which is distance. It could be a hectoliter, which is volume, right? But the prefix is hecto, and the scientific notation would just be 10 squared. So 8th graders, you can go ahead and write that in. Then we have deca. And right underneath that, you guys all have for prefix, liter, gram, meter. What that really means is there is no prefix in that section, okay? It's just one. If you look at the meaning, it's just one. So that means it's whatever measurement we are using. So you have liter, gram, and meter. If we're looking at liter, we're talking about a volume. If we're looking at gram, we're talking about a mass. And if we look at meter, we're talking about a distance, right? And so we're just assuming that it's going to be one of whatever those are that we're talking about. Now when we add deco or we add deci or centi or something like that, we're talking about making that unit larger, or we're talking about making it smaller. And if you look at that, you can tell that the larger units are going to be at the top, right? You see kilo is 1,000, hecto is 100, deca is 10. And even though we don't work too much with the metric system, I think most of you would know that 1 kilometer is way bigger than 1 millimeter, right? And we see again at the top kilo, and at the bottom of that chart is milli, okay? If there's any confusion with this whatsoever, please just fill in your table and we will deal with this later, okay? I'm trying to get through all this section of notes, and like I said, we'll dive in kind of to each section at a time. Okay, so continue down this list, fill in the rest for you 8th graders with your abbreviations and your scientific notations for deci, centi, and milli. Understanding that underneath the liter, gram, meter, where I put base unit on your notes, that whole section is going to be smaller than what that unit is. It's like a fraction of it, okay? So some of you are probably thinking, why do we use the metric system? I'm so confused by this already. We use it because it easily converts by a factor of 10, right? And if I can refer back to this real quickly, where the meaning is, it shows it in scientific notation here, but your meaning on your paper shows how it's by tens, right? It's a lot easier to think, okay, if I have a centimeter and I'm converting to millimeters, I'm just going to multiply by 10 because there's 10 millimeters in a centimeter. And that's how every prefix is dealt with in the metric system. But when we go into our system, it's really kind of weird. The imperial system will say, oh, 1 foot is 12 inches, right? Why isn't it just 10 inches? Then all we have to do is move a decimal over when we convert and we do math with it. But you guys are all set up. You're used to talking about it in that way with feet and inches. You know, generally speaking, how big those are, and so your brains are just kind of set on that mode. More with that later. This is how we convert as we move through the metric system, and I'm just including this in the notes because we'll actually refer back to this when we get into converting within the metric system. But as you can see here, if you start right in the middle, you've got liter, meter, gram. That's your base unit, whatever you're measuring with. And you can see the arrow on top, the blue one. It says as you go up the steps, you divide by 10, right? So if we have a meter and we're going up to deca or hecto or kilo, we're going to divide by 10 each time we move up. And the black arrow going down the steps shows us that as we go down, we multiply by 10. This will come in handy. We'll look at this chart, 8th graders, when we start actually converting within the metric system. All right, different types of measurements. So this is what you guys should have brainstormed earlier. All different types of measurements, the way that we measure things in our world. The first one is length. It's a measure of distance, right? So the imperial system says inch, feet, yard, mile. Strange little fact about that, the way we got the unit of feet is the king at the time, I think it was like King Louis or something, decided, hey, measure my foot. As big as that is, let's call that a foot. And that's actually what they did. So 12 inches, 1 foot, that was the size of the king's foot at the time, right? Kind of crazy to think that that's where it actually came from. But our system, inch, feet, yard, miles. Again, this is really strange because we don't use those units of 10. There's 12 inches in a foot, 3 feet in a yard, and then 5,280 feet in a mile, which is like, I forget, 1,800 yards or something like that. Somewhere around there. Some of you might do the math or some of you might already know it. But as you can see, all those numbers are really strange and it's tough to convert from one unit to the next. You have to just memorize those numbers. The metric system uses the meter. That's it. And then if we need to deal with large units, like we're going long distances, they'll deal with the kilometer. Or if we're talking really, really small sizes of something, then we would use centimeters or millimeters. Time is another measurement that we put on things, right? So time, the metric system is seconds, and that's actually the one metric system that we do use in the US. We don't, as far as I know, have any imperial system for measuring time. It's just seconds. The mass of something. So mass can be a really difficult concept to understand. The mass is a measure of how much matter is in an object, or if you have a hard time understanding what matter is, or you don't just really understand that definition of it, it's just how much stuff is there, right? Like how much actual stuff is in an object. And so the difference between mass and weight we'll discuss in just a second. It kind of seems like the same, but it is different. The mass is a measure of how much matter is in an object. And I put an elephant and a peanut in that picture because an elephant is way bigger than a peanut. There's a whole bunch more stuff in an elephant than there is a peanut. We can also say it does correlate to weight in a sense, but right now we're just talking about how much stuff is in an object. The metric system says grams. The imperial system uses ounces. Anybody know how many ounces are in a pound? Okay, in case no one knows the answer, is 16, right? 16 pounds in an ounce. Again, it's just really weird. 16, as far as I know, there's nothing else where we convert in the imperial system that has 16s. We have 12 feet or 12 inches in a foot, and 3 feet in a yard, and just all random numbers. Now, the weight of something is the force on a mass that's being measured, and that force is due to gravity. So an elephant standing on Earth may weigh 8 tons, right? A ton is 2,000 pounds. So 16,000 pounds. However, if you take that elephant and you stick it on a rocket and you fly it up in outer space and it lands on the moon's a lot smaller than Earth. Its gravitational pull is much smaller. So the force exerted on that elephant by gravity is going to be much less. So even if you put it on a scale up on the moon, it's going to have a weight, but it's going to be much less of a weight because its force due to gravity is less. Okay, its mass doesn't actually change. The elephant being flown up into space and landing on the moon, it doesn't necessarily become smaller or larger or anything like that. There isn't more stuff in it or less stuff in that elephant. It's still going to be the same elephant, but its weight is going to change. And actually the same with you guys. Anything that has a change in the force of gravity is going to weigh differently, okay? So the imperial system, the one that we're on, is pounds, ounces, tons. The metric system uses grams. And if we're talking big weights, they would say kilograms. Or they may go even further, megagrams. And that's not on your chart, but that's a larger measurement or a larger prefix. Again, if you don't understand that, if there's something you don't understand in this section, we'll go through and we'll do measurements of each little bulleted point here we're talking about. So we'll do a day of lengths, and we'll do time, and we'll do mass and weight, and the next one area. We'll have days that we work on all these things, and I'll try to drill that into you guys a little bit better so you understand it more. The area is the amount of surface on an object, okay? So mathematically, we just say area equals length times width, and that's really simple when we have something like a cube, well, a square or a rectangle. A cube is three-dimensional, so that would be volume. But yeah, when we have something like this, that's really simple, length times width. When we get into different shapes, there's different ways to measure that. But in the imperial system, it's feet squared. And I wrote this into your notes here. Try to think of this, because a lot of people have a hard time remembering feet squared when we're talking about the area of something. But area is length times width, right? So I put here IE, which means example, 3 times 3, right? 3 times 3, we know the answer is 9. But another way of saying 3 times 3 is 3 squared, right? And so when we get into units, if we had 3 feet being multiplied by 3 feet, we would multiply the 3 by 3. But we would also have to multiply the feet times feet. And so, as I put over here after the ... we have feet times feet There's no number that correlates with that, but we can say it's just feet squared, right? Just like we did with 3 times 3. We said 3 squared. Now feet times feet is feet squared. So that is the unit that goes along with it. The imperial system, feet squared, yards squared, inches squared, etc. When we're talking about homes, we talk about square footage and things like that, right? The metric system would be square meters. And it's the same exact concept, okay? Because we're multiplying numbers, we could say 3 times 3. In this case of meters, we would say 3 meters times 3 meters. So meter times meter, we represent as meter squared. Volume would be the next one. This is kind of a fun one. There's a lot of different ways to measure volume. And when we talk about gases, when we talk about liquids, they take the shape of their container. And so the volume can be different as far as measuring it, right? Volume is just the amount of space that something occupies. So some things we can compress, or some things will expand and they actually change their volume. If we take a basketball and we put it outside and it's below freezing at night, what's going to happen to the volume of that basketball? Some of you are probably saying it's going to shrink up, right? So it's going to get a smaller volume because it gets cold. The molecules inside of that basketball shrink up a little bit, and so it actually occupies less space. Does it mean there's less air in there? No, it doesn't mean that. If you bring it back in to a nice warm temperature and give it some time, it should warm up and it should expand back out as it was before. So the volume does change even if the mass or how much of that thing is there. Even if that does not change, the volume can change. Volume, when we're talking about solids, is length times width times height. So there's our cube reference. If you take like a dice or a die, if you take that, you could, because it's almost a perfect cube, you could measure length and width and height, and you could get the volume of that. If it's a liquid, we measure it in containers, right? So scientifically, we could use a graduated cylinder or a beaker or an Erlenmeyer flask or a lot of different things. We use gallon jugs at the grocery store. We use fluid ounces, which are different than ounces. Fluid ounces, those are imperial system. Another thing that we measure is temperature, it's the amount of heat in an object, right? So something really, really hot has a whole bunch of heat in it. Something really, really, really cold has just a little bit of heat in it, okay? And I know that seems kind of backwards, but temperature is a measure of heat. So we can't say, oh, this is only 5 degrees, so it has a whole bunch of coldness in it, right? We use coldness like to describe things, but coldness is not like it's not a noun in the sense that it's a thing. It's just lacking heat, okay? But everything has heat in it. The imperial system is measured in degrees Fahrenheit, right? F. So we say, oh, it's 60 degrees outside. It feels great today. The metric system would say, oh, it's 15 degrees outside. It feels great today. Because Celcius is a different measure, right? This thermometer here shows us Fahrenheit and Celsius, and it kind of shows you going across what those temperatures would be. So 60, yeah, it's like 15 or 16 degrees or something in Celsius. There's also degrees Kelvin. That's a scientific measurement. It's only used in science. And when we say something has no heat in it whatsoever, then it is absolute zero. That's its temperature, and that's measured in degrees Kelvin. That's really weird stuff. That's like only out in space, okay? So we don't really deal with that too much. It is something I'd like to put on your radar just because in the future, maybe in high school, you may have things that deal with Kelvin when it comes to temperatures. But we deal mainly with Fahrenheit, and some of you 8th graders, you're going to be dealing with Celsius too when we work with the metric system. The velocity is distance covered in some amount of time. And on your paper, I think this didn't copy so well. It's the speed, or we could also say rate, okay? And those are different. If you talk about that stuff mathematically, or in math class, you'll realize that speed and rate are a little bit different. But for all purposes right now, is distance divided by time, okay? That's what it is. Velocity, and we're going to say speed and rate are the same thing. Velocity is distance divided by time. The imperial system says miles per hour, or if we're measuring like the velocity of a stream, we might say feet per second or feet per minute or something like that. The metric system doesn't use our same system, right? So they would talk about meters per second or kilometers per hour. Some of you have maybe noticed, I know you guys aren't driving yet, but some of you maybe noticed in a vehicle that when you have your speedometer there on the front dash, right, it'll say 0 all the way up to, I don't know, 100 miles per hour or something, 120. It also has another system there. It's not just the speed limit in miles per hour, it also has kilometers per hour. So that's, again, the metric system. Or if you've driven through Canada, you've seen speed limit signs there that were not miles per hour, but kilometers per hour, which is really confusing. And that's it, guys. Make sure that you have everything filled in through your notes. If I was moving too fast at any point, go ahead and go back through and get those filled in, please. When you're finished with that, please make sure that you turn it into the box, and I will get those graded and get them back to you as soon as I can next week. And I did want to also touch on that because I haven't graded or I haven't put in grades. I've graded about half of your assignments, and I'm going to continue grading, and I'll get those into the grade book as soon as possible. I'd like to by the end of the weekend, all right? So everything should be updated and all good by the end of the weekend. That's my plan. Good luck with everything, guys. I hope you have a good week.